We have two open ends that I want to close. One is I talked about mass transfer as a mechanism for generating blue stragglers, and the other is that I sort of said that the end of our sun, after the beautiful light show that is the planetary nebula, is a slowly cooling solar mass, Earth-sized chunk of carbon that it will eventually, as it cools, crystallize. So that's a pretty nice diamond in the sky, but is a white dwarf really the end for a star? It will be for our sun, but it need not be. There's still life in them that are white dwarfs, despite the fact that they're fusion-wise completely inert. And the trick is the phenomenon of mass transfer, so we need to understand it. And the mathematics is due to our old friend Roche, who we all love and remember for his work on tidal forces. And so thing to remember is that the real question we want to ask in a binary system, of course, every object in a binary system is in some sense rotating, orbiting both stars. Each star is orbiting the common center of gravity, and if you throw a rock in there, it'll also orbit in some complicated way both stars. But we want to describe this in a way that gives us a sense of what orbits which star, which matter is bound to which star, and the complication is that the two stars themselves are rotating. So if you wanted something to be sitting next to a star, it has to not just orbit that star, but also follow it on its orbit around the common center of mass. And this is the problem that Roche addressed, and it turns out that if you ask the question, imagine the whole universe rotating with this system. Imagine that the stars are in circular orbits, and sit somewhere in this rotating universe and drop a rock and ask where it will fall. The combination of gravity and the rotational motion is described by this Roche potential. Here is the Roche potential drawn for a combination of two stars relatively close to each other, one of whom has twice the mass of the other. And so this surface here is the potential, so that if you drop something here, it will slide that way. If you drop something here, it'll slide down into the star. There's a complication that the rotation introduces, just like the rotation of the Earth, something called the Coriolis force, for the same reason that winds and artillery shells in the northern hemisphere turn to the right. If we imagine that this is the direction in which the stars are orbiting, then indeed everything will turn to the right, so that, for example, a stone left here will not actually fall down the potential, but will go into some kind of crazy orbit around this so-called Lagrange point. But that's not what interests us. The point is that this allows us, by drawing a particular level surface of this potential, particular region where you can move from one to the other without experiencing any gravitational force, is this particular surface that meets itself at a point, this top of this saddle right there, or the bottom, depending which way you count it in a saddle. And this divides the region near the stars into two lobes, the larger of which corresponds to the more massive star. The point in between where the lobes meet is not quite the center of mass. It's shifted closer to the, notice it's closer to the lighter star than it is to the more massive star, whereas the center of mass is closer to the massive star. But the idea is that this is the region in which the gravity of this star dominates. This is the region in which the gravity of this star dominates. If you drop something from here, it'll go into orbit around this star. Drop something here, it'll go into orbit around this star. Drop something here, and it can move around in an orbit like this, which is some complicated orbit around both stars. So typically, for two stars in a binary system, this is a very interesting thing if you're going to add planets, for example, into the system. But why is this interesting when you have two stars? Well, here's the picture. And Algol, our friend Algol, the ghoulish star in Perseus, is the prototypical example. And Algol presents astronomers with a puzzle. We can appreciate the puzzle now. Algol has two members, 3.6 solar mass main sequence primary and a 0.79 solar mass subgiant secondary. That can't be right. The reason it can't be right is because the two members of a binary would have formed from the collapse of the same cloud absorbing the angular momentum. And if they formed together, then the more massive primary should have evolved earlier. How is it that a 3.6 solar mass member is on the main sequence while the less massive secondary is already done with its main sequence life and is already a subgiant? That's a problem. the hint to the answer is that Algol is a very close binary system. The distance between the two stars is 0.062 AU. That's only twice the distance between the Sun and Mercury. And both this star, because it's a massive main sequence star, and this star, because it's a subgiant, are much larger than the Sun. And so imagine sticking another sun twice as far out as Mercury is, then make them both big. These stars are almost touching. The answer to the Algol puzzle is that, just as we talked about for blue stragglers, B actually started out, what is now the secondary, started out as the more massive star. So how come it's less massive now? Well, as long as they were both main sequence stars, they orbited each other, and each lived within its Roche lobe, and so the atmosphere of each was part of a well-defined object, the star. But then, when B turned into a subgiant and started to puff up, it leaked. Its outer atmosphere leaked outside its Roche lobe. When it leaked outside, some of it was captured onto A, which is now gaining mass, while B loses mass, which means the Roche lobes move. B's Roche lobe gets smaller because it's less massive. A's Roche lobe gets larger because it's more massive. And eventually you get a runaway process of mass transfer from B to A to the point where now a large fraction, remember B was more massive than A initially, a large fraction of the mass of star B has been transferred to star A, which is now more massive. And this matter, in the same way that we'll see later on, comes in with a lot of angular momentum from the rotation, so it forms an accretion disk around star A, and then as material loses angular momentum and energy, it spirals in and eventually falls onto star A, and star A's atmosphere is increasing while star B is losing mass. So this is a curiosity. It's a very interesting phenomenon. It's fun that we can understand both the riddle and its solution. What has this got to do with, and it's clear how this might resolve the issue of blue stragglers. If you start with a star that's not very massive, then it sucks a lot of mass from a binary partner. Then you would find in your globular cluster a star that is more massive but still on the main sequence because it used to be a not so massive star and evolved very slowly. So far so good. What has this got to do with white dwarfs? Well, imagine if in a close binary system the more massive partner evolves, finishes its main sequence life, ejects a planetary nebula, and leaves us with a white dwarf, while the less massive partner is still on the main sequence. Eventually, the less massive partner also will bloat up and become a giant, and when it becomes a giant, the less massive partner now might extend past its Roche lobe, and this time its partner is a white dwarf. So that means that matter can be transferred. We can have mass transfer from the less massive partner to, remember, now the white dwarf is probably the less massive object because it lost all of its atmosphere, but onto the white dwarf, and models show us that in a close binary, that rate of mass transfer can reach 100 millionth of a solar mass per year. That's a substantial rate of mass flow. What happens to this gas? Well, when it falls onto the white dwarf, this is the white dwarf acquiring a little bit of a hydrogen atmosphere. Of course, this is nothing like Earth's atmosphere because gravity is hundreds of thousands of times more intense at the surface of a white dwarf. And so, remember, this is an Earth-sized object with solar mass. And so the hydrogen is immediately compressed to degeneracy and heated by the immense surface gravity. So you have this very tightly bound degenerate atmosphere. Moreover, it turns out that it's important that at its base there's turbulent mixing because of the heating, and that enriches the gas with carbon, nitrogen, oxygen, the materials out of which the white dwarf is made. And then what happens is that when the white dwarf has accumulated about a 10,000th of a solar mass of this atmospheric hydrogen, the bottom, the base, the temperature at the base, at the bottom of this atmosphere, which is very, very thin in metric terms, but contains a 10,000th of a solar mass, the temperature reaches the magic number 10 million Kelvin. When the temperature reaches 10 million Kelvin, you can start efficient CNO hydrogen fusion, the CNO process, and again we have a degenerate atmosphere. Because it's degenerate, it does not expand when fusion starts, so the fusion is explosive, and essentially the entire atmosphere fuses to helium simultaneously, this, well, not the entire atmosphere, only about 10% gets diffused, because after 10%, the temperature rises to 100 million K, and the thermal pressure overcomes degeneracy pressure. At this point, the luminosity of the object can reach 100,000 solar luminosities. This is 100,000 times as luminous as the sun, and it's not like the helium flash because it's not hidden. It's exposed. We will see something with 100,000 solar luminosities. Once you reach that temperature, radiation pressure ejects the remainder of the accreted material. The total energy released is on the order of 10 to the 38th joules over a few months. That, if you think about it, is comparable or slightly more by a factor of 10 than the total energy the sun will release over its entire history. And this can recur, when mass reaccumulates. So novas can recur every 10,000, a few tens of thousands of years. And this ejected matter initially glows at about 9,000 Kelvin, so it has a characteristic high-frequency light signal. And these novae are pretty common. We see a few per year in the Milky Way, but we don't see far into the Milky Way because of dust obstructions. We see better into, say, our neighboring Andromeda galaxy, M31, and there are about 30 novae per year detected in M31, and the citizen scientists are instrumental in discovering these as well, the variable star observers. Here's a visible light image of a nova that exploded in Cygnus in 2010. And so this is 3 days prior, and this is 3 days later. You see why the name nova was given. If the star was too dim to be visible before, this presumably is not the white dwarf, but its partner. But a star could be too dim to see, and then suddenly it's 100,000 solar luminosities. You certainly notice that object at great distance. Nova for new star. These novae leave behind interesting remnants that are being carefully studied. All this structure in the ejecta. This is the ejecta still glowing many years after the nova exploded, and in the center the white dwarf is getting ready to do it again. And so white dwarf need not be the end of the road if you have a partner to mooch off of. Now, this brings up an even more interesting possibility. Nova is a very cool object and very interesting and brilliant, but there's something even more exciting, which goes under the name supernova. What is super about a supernova? Well, supernova is the answer to the question, a type 1a supernova, is the answer to the question, well, wait a minute, so accretion is adding to the mass of a white dwarf. What happens if you add so much mass that it exceeds the Chandrasekhar limit? Remember, a white dwarf cannot have a mass more than 1.44 solar masses. It would collapse. As modeling, and this is a difficult problem, shows, the mass of a white dwarf never doesn't exceed 1.44 solar masses. As the mass becomes close to the Chandrasekhar limit, the white dwarf compresses. Remember, at 1.44 solar masses, it would have zero radius and zero volume. So as the mass increases, pressure and temperature in this compressed, degenerate carbon-oxygen object are increasing, and eventually a turbulent convection phase starts out that leads to the ignition of carbon fusion. And again, you're in degenerate matter. The heating from the fusion does not lead to expansion, so we get a violent explosive process which fuses a substantial fraction of an entire solar mass of carbon within a few seconds. Oxygen fuses too, although less completely. This heats the object to temperatures of 1 billion Kelvin. It releases a total of 10 to the 44 joules. That's like 1 million novae. This deserves the title supernova. It blows the star completely away by releasing a shockwave that ejects material at very high speeds throughout the neighborhood. Typically, the donating partner, if there was a partner that was from which the white dwarf was accreting, that partner will be blown away at high speed and become what's called a runaway star. The luminosity of the supernova can be 1 billion solar luminosities or more. That's characteristic of the luminosity of a galaxy. So you have a very small target, a point object, glowing with the luminosity of a galaxy. You can see these way far off in the universe. And they're characterized by a spectrum that has absorption lines of silicon, which is found inside the white dwarf and is formed by fusion, but very few hydrogen and helium lines, because this was formed in an object which is essentially carbon, nitrogen, and oxygen. And the shock wave drives fusion to heavy elements from carbon to nickel to iron and beyond. Uranium and heavier elements are produced in the shock wave driven by a supernova. This creates a lot of radioactive nucleotides, and their decay sort of contributes to the late time luminosity. So the energy of the shock wave, some of it goes into forming these radioactive nuclei, and they release their energy over years, over the next few months or a year, and so we can trace the half-lives of the isotopes that created it by tracking the light curve. Very exciting objects. More exciting than you might think. What do we know about them? Well, understanding this explosion is difficult. Understanding how they happen is not obvious. So we know that a type 1a supernova happens when a white dwarf approaches the Chandrasekhar limit. Where did it get its mass? There are two possible suggestions. This might remind you of the blue straggler debate. One is called the SD, or single degenerate model, where the donor is a main sequence or giant star in a very close binary pair with the white dwarf, and the donor exceeds its Roche lobe, and that is how matter accretes onto the white dwarf. You have to be careful. You have to make sure matter accretes fast enough that the white dwarf does not have time to nova it away before it approaches the Chandrasekhar limit. The competing proposal is what's called the DD, or double degenerate model, where the donor is another white dwarf, and for some reason, imagine two white dwarfs orbiting each other. Well, they're going to orbit each other. Nothing's going to happen. White dwarfs don't grow outside their Roche lobes. They're tiny. But if you manage to make them orbit so close that their distance was of the order of their size, that's the Earth's radius. That's two stars orbiting each other within an order of magnitude of the Earth's size. How do you do that? Well, if you only had some friction that could slow them down. But there's no atmosphere because it's a white dwarf. We'll learn later that there is a kind of friction that could slow them down and bring them into this very close orbit. When they get close enough, the gravitational forces of the slightly more massive one will rip apart the less massive one. You get dramatic mass transfer through the Roche lobe, and essentially you have a merger of two white dwarfs. And which of these is the correct scenario? Recent observations suggest that both occur, but the tide is turning. The single degenerate was the older model, and more people are convinced that this at least has to play a role. We'll see some evidence for that in a minute. The nature of the explosion itself is hard to understand. It's very hard to model such a non-equilibrium, turbulent process. For example, it's not even clear whether fusion proceeds as burning, deflagration, or an honest detonation, where the speed with which the fusion reaction expands is faster than the sound speed, which is quite high inside this dense degenerate object. Is there an actual triggering of the initial explosion by a flash of degenerate helium in the atmosphere, or does it start, as I suggested, by internal carbon-oxygen fusion? But there's one important fact, and the fact is observational and very critically important, but we understand what's going on. Essentially, no matter how you got there, a type 1a supernova is the complete fusion of an object made out of carbon and oxygen whose mass is 1.44 solar masses, or essentially as close to the Chandrasekhar limit as this object can get. So type 1a supernovae are essentially all the same. And indeed, when they occur in clusters and galaxies to which we know the distance, we can compute their luminosity by measuring their brightness and comparing the distance that we know, and indeed their luminosity is almost exactly the same. Amazingly uniform objects compared, say, to the differences in luminosity among stars. And in fact, if you make some corrections based on the shape of the light curve, then you can actually use these things as standard candles. Here's how you build a standard candle. Here are the light curves of several supernovae. You can see that this one was considerably more luminous than that one. But after making corrections for subtleties in the spectrum and the shape of the light curve, You put them all on this one exact curve. This is brilliant because this means if you measure a type 1a supernova at its peak, then you know the luminosity of the object you measured. And this is an object with a luminosity of a billion suns. So you can see these things way far off in the universe. These are measuring sticks for large distances, and much of what we've learned about the structure of the universe at large distances is due to this understanding of type 1a supernovae being a standard candle. We'll come back to that aspect. I was talking about the double degenerate model. These are recent observations that lend it some credence. The image on the left is a beautiful image of the remnant of a supernova, and what is observed is that we can pinpoint the direction in which we should have seen the white dwarf remnant. The partner remnant, had there been a partner, the white dwarf blew itself apart. The remnant should have been there, the other star, had it not been completely ripped to smithereens. And sensitive searches have found nothing there. An even more exciting version of this is these X-ray data from the SWIFT satellite, where basically they took 53 type 1a supernovae and superposed them on top of each other so that their centers completely coincide and look for the X-ray signal. And what they find is nothing. In other words, were there a surviving partner to these supernovae, then that partner should have been heated to extremely high temperatures by the explosion. You would have expected an X-ray signal. There is none. What that means is that the partner was completely destroyed. These are both evidence, but not conclusive for the DD model, computing the number of supernovae we see, comparing it to the probability of binary white dwarf pairs, still suggests that the single degenerate model has to make a contribution to these amazing objects.